Welcome back to the Lowdown on Physics. Today we're looking at Newton's laws of motion and how they describe the concept of force and how that can be used to explain why an object moves the way it does. Einstein's theories have superseded these laws, but for most applications, particularly those at low speeds, these laws are still precise enough. Newton's first law describes what happens to an object when a non-zero or an unbalanced net force acts on an object. It says that a body will remain at rest or move at constant velocity unless acted on by a force. The constant velocity one is where it'll come up. It'll ask for the force that's acting when an object's moving at constant velocity. So usually it's one of those trick questions where the answer is always zero. Okay. Law number 2. This is basically explaining how a body responds when that unbalanced force is acting. And basically it says acceleration depends on two things, the force and its mass, or inversely proportional to its mass. That means that the lighter the mass, the greater the acceleration. The greater the force, the greater the acceleration. Newton's third law says, or looks at action-reaction pairs. And the most famous of his laws says for every action there is an equal and opposite reaction. So you've got force that is acting from A onto B is equal but opposite, indicated by the negative sign of that B acting on A. It's important to remember that the action-reaction pairs are acting on different bodies. So for example, if you think about being hit by a car, you apply equal and opposite forces to each other, but because the mass of your car is significantly greater than the mass of the person, the acceleration will be quite different, which is Newton's second law. The person will obviously accelerate with much greater acceleration than the car will experience from that interaction. Okay, let's look at an example here. In this example, we've got a man dragging a bag across the floor. It's moving at constant velocity. There's a very key word. Now there's a frictional force of 100 newtons and it's being pulled at an angle of 25 degrees to the horizontal. And then three things that we need to calculate. So, given the question, I'm going to represent some things with a diagram. Here's my bag. We've got a frictional force of 100 and we've got the force of the man at the angle of 25 degrees to the horizontal. So firstly, net force on the bag, it's constant velocity, so there is a zero net force. That's a 1 mark question. Anytime you see a calculation question that's 1 mark, usually it's a straightforward, simple application of some theory. So that's just a F net is zero because it's constant velocity. Part B, we've got the net force that this man is exerting. We want to know F. What we know is that this horizontal component here is 100 newtons. So F cos 25 equals 100 newtons. So if we bring up our calculator, then we've got F must equal 100 divided by cos 25. So we have, let's put that into a decimal form, we have about 110 newtons of force that's applied. The majority of that force is applied in the horizontal direction, but there is some wasted force as such in the vertical direction. So if we have 110 newtons being exerted on the bag, then the bag must exert 110 newtons back on the man. So that's an equal and opposite reaction force. As we saw in the previous example, friction and tension provide external forces that we need to account for. Generally, we are going to use an equation where we're just calculating a net force. Basically, we add the forces that are going in a positive direction or assisting the motion. We subtract forces that are retracting from that motion. Basically, I always start just by drawing forces on the diagram. So we'll have a look at an example now. In this example, we have a car that starts from rest and accelerates at 5 meters per second squared. The mass of the car is 1,000 kilograms, trailer is 800 kilograms. Now what happens, which is interesting, is we have friction or total resistance that increases as the speed increases. So this is probably one of the more realistic questions that you'll see in Unit 3 Physics. The first question asks us to find the value of T, the tension in the coupling of the trailer when it's travelling at 20 meters per second. Remember, it was accelerating, so it's not constant velocity. So we do have a net force in this scenario. So we start by drawing a picture. So we've got our car, we've got our trailer. We have the tension in the trailer coupling that's pulling the trailer forward. We also have all of the resistance. In questions like this, it's often a whole lot easier to analyze it piece by piece. So analyze one carriage of a train or one trailer, or just the one unit at a time. Analyze the forces and the relationship with the net force for the one object. So in this case, we've got the net force is the sum of the positive forces, in this case tension, minus the resistance forces. So F net, that's MA. We had a mass of 800 and it's accelerating at 5, so F net's 800 times 5 minus, is equal to tension minus, at 20 meters per second, we've got roughly 60 newtons of resistance for the trailer. So tension is 400, rearranging 4,000 plus the 60, it's 40,060 newtons. Find the force, the driving force applied by the car to cause this acceleration. So again, here's our car. We've now got a driving force. We have the equal and opposite force of the tension from the trailer, plus, didn't put it on, plus we have some drag caused by our resistance. So in this case, F net, which will be MA, equals the driving force minus the tension minus the frictional resistances. So we've got 1,000 times 5, that's MA, equals our driving force, minus the tension, equal and opposite from the previous question, minus our frictional force. At 20 meters per second, the car's got 200 newtons. So rearranging, we get 9,260 newtons. Oh, there it is. Okay, it reaches 25 meters per second and travels at constant velocity. What's the value of the tension now? Okay, what we've got to remember is that at constant velocity, all the forward forces must add up to the sum of the backward forces. So there is a net force of 0, so tension will equal the frictional forces. So at 25 meters per second, it's roughly 80 newtons.